In the second part of our lecture, we will discuss reactions of carbonylic compounds. First type of reaction, it is nucleophilic addition to the carbonyl group. Now we have to talk about addition of alcohols. This reaction is possible in the presence of mineral acids with alcohols. RO part of alcohols is added to carbon, where we have partial positive charge, and hydrogen is added to oxygen, and we obtain hemiacetal. The next reaction that is possible in the same reaction mixture isn't nucleophilic addition to the carbonylic group. This type of reaction is very similar with with reaction of ethers formation. As a result, is formed acetal. Here, free OH group reacts with one more molecule of alcohol, and we obtain a product with two residues of alcohol. This reaction is very important in the nature, where this reaction occurs by some tautomeric interconversion of carbohydrates. Next reaction in this group, it is addition of water. The same OH group of water is added to carbon here and hydrogen to oxygen, and we obtain hydrates. As usual, these compounds are not stable. They can be formed reversibly in water solution of carbonylic compounds, but in some compounds, this type of this second type of compound, the second hydrate, stable, and here are formed stable compounds. Example of such compound is 3-chloroacet aldehyde hydrate. Another name for this compound, chloral. Chloral was used as sedative medicine. Nowadays, it's not used for people, but it's used in veterinary medicine as narcotic and anesthetic compound. This compound is stable because of presence of three chlorine atoms with negative inductive effect, and they take electron density from this carbon and make this hydrate more stable. Next group of compound is addition of Grignard reagents. We have discussed this reaction with you when we discussed the reaction of alcohols formation. So depending on the type of carbonylic compounds that we need, the type of alcohols that we need, we use different carbonylic compounds. First of all, generally, how is formed a product in this reaction? So this it is alkyl substituent or aryl substituent, and it is added to the carbon. And the second part of molecule, magnesium and the halogen atom is added to oxygen. And we obtain such an intermediate that by hydrolysis of hydrochloric acid is converted to the alcohol. And now more detail what alcohols can be formed during this reaction. So if we take formaldehyde, as a result of this reaction is formed primary alcohol. If we take another aldehyde than formaldehyde, then as a result is formed secondary alcohol, and with ketones, this reaction results in tertiary alcohols. So it's very convenient method to get different types of alcohols. One more similar method that is possible for carbonylic compound addition nucleophilic, it is addition of carbonyl groups. addition of organolithium compounds. Similarly as with Grignard reagent, this red part is added to the carbon and sodium is added to oxygen. And this reaction the same as convenient method to get alcohols with the triple bond in the molecule. Addition of hydrogen cyanide. One more method of one more reaction of nucleophilic addition. As a result of this reaction, we obtain added cyano group to the carbon atom and new H group. As you see, here is hydrocarbon chain, one carbon longer, and this is convenient method when we need to make this hydrocarbon chain longer. And this method can be used the same for carbohydrate synthesis. One more huge group of compounds that can be added to the carbonylic compounds. These are nitrogen nucleophiles. In this group, we have many diverse compounds that can be added to the carbonylic group, and the general mechanism is shown here. First of all, is added, we observe addition nucleophilic. So this part where is nitrogen is added to the carbon, and hydrogen that is blue is added to oxygen here. But this compound is not stable and spontaneously is evolved with water, and we obtain compound with a double bond between carbon and nitrogen. And depending on this R, we can have diverse products. For example, if we take ammonia or imines are formed imine. Here is general form of this compound. If we take hydroxylamine, is formed oxime. If we take hydrazine, is formed hydrazone. And if we take phenylhydrazine, is formed phenylhydrazone. And there are much more compounds that are not shown here. But the same, this reaction is convenient method for identification, especially for ketones. For example, reaction with hydroxylamine can be used because ketones in this reaction give solid products, and these products can be identified by temperature of melting. And this gives possibility to detect what ketone do we have. Some specific reactions occurs by addition of ammonia to the acetaldehyde. So first of all is formed compound and then is evolved water and is formed ethanamine. But spontaneously this compound can be transformed to the acetaldehyde ammonia trimer, and this compound is more stable. So this reaction is specific for acetaldehyde. And similarly, some specific reaction occurs by reaction of formaldehyde with ammonia is formed such an heterocyclic compound with 4 nitrogen atom, and this compound is has structure like an adamantane. Adamantane, as you remember, it is a carbocyclic compound that belongs to the group of cycloalkanes. And this compound is used as antiseptic for outside usage, and the same for treatment of urinary tract infections. And the same, it can be used in the form of cream or spray for a treatment of excessive sweating and unpleasant odor. One more specific reaction for formaldehyde, it is formation of a polymeric compound by cooling of its solution. Uh, Trioxane can be formed from formaldehyde by higher temperature. By lower temperature is formed para-formaldehyde. This is polymeric compound that can be easily converted backward to the formaldehyde by heating in the presence of small amount of mineral acids. And trioxane it's compounds that can be used the same way by hydrolysis. It can form formaldehyde. And similar compound can be formed from the acetaldehyde by cooling to 20-degree. Solution of acetaldehyde is formed paraldehyde, and by cooling to the 0 degree is formed metaldehyde. Paraldehyde is product of 3 molecules condensation, and metaldehyde is formed by condensation of 4 molecules of aldehyde. Next type of reaction that is possible for carbonylic compounds, it is reduction. As convenient reductor can be used, reductors can be used lithium aluminium hydride or potassium borohydride. They both are able to reduct carbonylic compounds to the alcohol. The mechanism is shown on the screen. Some specific in reaction with sodium borohydride is that this compound is more selective. An example is shown here on this screen. If you see, here is double bond and it's left untouched after the reaction with sodium borohydride. With lithium aluminium hydride, this double bond, the same, will be reduced. Now about oxidation of carbonyl compounds. By oxidation of aldehydes are formed carbonylic acids. As reductors can be used potassium permanganate, chromium oxide, silver oxide, and many other oxidators. Here are shown some examples. For example, with chromium oxide that has name Jones reagent, oxidation of long chain aldehyde leads to acid. And similarly here, aldehyde group is oxidized, but please pay attention, double bond is untouched in this reaction. Silver oxide is expensive reagent for synthetic processes, but it can be used in specific test for aldehydes. This test has a name after Tollens. Tollens silver mirror test or silver ammonia complex anion test. So this complex anion is formed in situ. It's mean in the moment of obtaining, we use it because we have to use this reagent immediately because it's unstable by storing and can be formed explosive products. So by this reaction, aldehyde group is oxidated to the carboxylic group. Silver that has oxidative state +1 is reducted to metallic silver, and the same is evolved with ammonia that can immediately react with carboxylic acid and water. This silver we can observe as a black precipitate, as we can observe as usual in case of formaldehyde, because it's very active reagent, or it can be observed as silver mirror on the tube walls. This reaction was used to make mirrors. As usual, was used glucose because this compound the same is heterofunctional. It has aldehyde group. But nowadays it's not used because of expensivity of silver, and the same because of this reagent is explosive. This test is true only for aldehydes. Ketones don't give this test. One more test that can be used for carbonylic compound for aldehydes. It is a reaction with Fehling solution. Fehling solution, this is complex compound that is formed by a reaction of tartaric acid with copper hydroxide. It's formed such a complex compound. This solution has blue color, and after reaction copper is reducted to the copper hydroxide. Here we have copper 2 valent, and here we have copper 1 valent. So copper is reducted, and then there's hydroxide is transformed to copper oxide, and we have Birk red precipitate. So we can observe this Birk red precipitate, or this color depends on the concentration of starting compound, aldehyde in the reaction mixture. Sometimes we can observe not red, but from brown to yellow precipitates. The same, this reaction with Fehling solution is true only for aldehydes. One more oxidation reaction that can be used as specific test for methyl ketones is iodoform test. Generally, it can be called haloform test. And the same can be used for methyl alcohols identification. In this test is used iodine and sodium hydroxide that by reaction form sodium hypoiodide, and this compound acts as oxidator and iodated this is iodated this metal group. We obtain 3-iodo derivative, but it's unstable and hydrolyzed quickly to form iodoform. Iodoform is a solid compound that is has yellow color, sometimes is white yellow, yellowish, and we observe it as precipitate in lab tube. Similarly, this test is possible for alcohols that have OH group at second position from the end of the hydrocarbon chain. For example, for ethanol, the same this test is possible, but methanol doesn't give this test. Acetaldehyde, the same, is able to give this test. This compound that is formed is used as antiseptic in medicine, for example in dentistry, and it has specific smell that sometimes people refer as that of hospitals. The same this reaction is possible if here we take bromine or chlorine. The same will be formed halogenated methanes. If we talk about oxidation of ketone, this process is more difficult. Not because it's not possible to do. There are many oxidators that we can use: potassium permanganate, potassium dichromate, and many another. But it's difficult sometimes to predict products of this reaction. For example, if we talk about butanone, here there are many products that can be formed. Here are shown places where can occur breaking of hydrocarbon chain, and the first part of molecules that can be oxidated forms formic acid. From this part is formed acetic acid. From this part the same as acetic acid formed, and from this part propionic acid. But nevertheless, this reaction of oxidation of ketones is used in industry for synthesis of acid. The same here are shown places where can occur this oxidation. As oxidator is used nitric acid in the presence of vanadium oxide. For ketones, possible ketoenol metabolism. Here is shown the general scheme. The hydrogen that is attached alpha carbon to the carbonyl group is able to transfer here to the oxygen, and here is formed a double bond. But some compounds, depending on the substituents that are surrounded this double bond, can be more stable in enol form. Such type of interconversion between two forms of one compound that can exist in equilibrium with each other are called tautomers, and this type of structure isomerism is called tautomerism, from the Greek tauto, the same, and meros, part. If we talk about aldehydes and ketones, so here is example. So for acetone, it exists in almost all in a carbonylic form, and keto form is existing in such and such. Nevertheless, this tautomerism gives possibility for very important reactions that are used in organic synthesis. And if we talk about acidity of this alpha hydrogens that are attached to the carbonyl group, so the second carbon of carbonyl group, it's hydrogens, so the acidity is higher for example, acetaldehyde. And if we compare with normal alkane, so acidity is higher, but it's much more weaker acids even than ethanol. And the reasons of acidity of alpha hydrogen in enolate anion. The first reason The carbonyl carbon carries a partial positive charge. Bonding electrons are displaced toward the carbonyl carbon and away from the alpha hydrogen. Here it's shown in the red. And this carbon takes electron density, and this hydrogen it's not so strong holded to this carbon. And the second reason of this acidity result an ion is stabilized by resonance, because here are two resonance structures. If we remove this hydrogen in the presence of base, for example, here are possible two resonance structures of this. And because of possible this tautomeric interconversion between carbonylic ketoform and enol form are possible aldol condensation. This reaction occurs between two molecules of aldehyde or ketone that react with each other. One molecule reacts as carbonylic compound with its carbonylic group, and another compound reacts as nucleophile. And we obtain the product of aldol condensation that has name aldol, and these compounds are 3-hydroxy carbonylic compounds. Here is shown the mechanism, how it's possible. In presence of base take hydrogen, carbon, and enolate anion. And at the second stage, this enolate anion with this alpha carbon attack nucleophilic group. And after reaction, we obtain product of nucleophilic addition to this carbon. It's formed bond between first carbon of one aldehyde or ketone and the second carbon of another compound, another ketone. And at third stage, from the water is taken one proton, it's added here where we have negative charge, and we obtain. And here is shown generally how if we have longer hydrocarbon chain, not only acetaldehyde is able for this reaction. So we can see that at third position we have OH group. At second position we will have substituent. This substituent and this substituent are as usual the same. These are some signs that give possibility to understand that we have product of aldol condensation. Sometimes this reaction doesn't stop at this stage. For example, by heating of such a compound, the result of aldol condensation of acetaldehyde is evaluate water or H from the third carbon atom and hydrogen from the second carbon atom is formed unsaturated carbonylic compound. In this case, it is crotonic aldehyde. And then this reaction is called crotonic condensation. It's a method of synthesis alpha-beta unsaturated aldehydes. If we talk about unsubstituted aldehydes, one interesting compound, the simplest, is acrolein. Acrolein is formed by heating of glycerol in the presence of some catalyst, in the presence of concentrated sulfuric acid, for example, and is formed acrolein. This compound is obtained by production of biodiesel from vegetable oils or animal fats. This compound is colorless liquid but it has a very acrid smell. And this smell is very similar with the smell of burnt fat. And this compound is used as herbicide and the same to control floating weeds. It is irritating, it produces tears. Lacrimators, these are lacrymators. These are compounds that can produce tears, so acrolein belongs to this group of compounds. And one more compound that belongs to the unsubstituted aldehydes is crotonic aldehyde. This aldehyde is obtained by the reaction of acetaldehyde in aldol condensation and next removing of water. We can say that it is crotonic condensation of acetaldehyde. This compound is used as a precursor for synthesis of sorbic acid. Sorbic acid, its salt, is used as food preservative, and the same it can be used as precursor for the vitamin E synthesis. Some specific reactions are possible for unsubstituted aldehydes. For example, addition electrophilic with hydrohalogens or with water. We observe addition against Markovnikov rule. This is explained by such an intermediate very stabilized another particles that we observe in the addition electrophilic of alkenes, unsubstituted alkenes. And as a result, we obtain beta substituted aldehydes. It can be, in this case, it is bromopropanol. With water, we obtain 3-hydroxypropanol. Reaction with cyanide is observed in carbonylic group. And we obtain hydroxycyanide of acrolein. Next reaction, it is similar with aldol condensation, the Tischenko reaction. The result reaction looks as a result of condensation of reducted and oxidated aldehyde that we take for reaction. For example, if we take acetic aldehyde, the product of oxidation, it is acetic acid, and the product of reduction, it is ethanol. And together they can, after condensation, make ethyl acetate. The same we observe in this reaction. And the catalyst in this reaction, it is aluminium ethylate. And the first stage of this reaction, it is addition of this catalyst to the oxygen of carbonylic group, and this formed an ion with negative charge at aluminium. Then this activated particle is attacked by one more molecule of aldehyde and is formed a product of addition with positive charge at carbon and negative charge at aluminium. And then after evolving of aluminium ethylate is formed, and this hydrogen is transferred to carbon with positive charge is formed ethyl acetate. So similarly, if we take propionic aldehyde, will be formed propyl propionate. With butyric aldehyde, it will be formed butyl butanoate. Some reactions can occur in alpha position to the a carbonylic group. In this group of reaction, we can observe many substitution reactions, for example, with bromine or with another halogen. The catalyst here is uh, mineral acid. So this reaction every time occurs at alpha position from the carbonylic group. A similar reaction we observe for carboxylic acids. The same in alpha position is possible CH acidity, and here is possible substitution with halogens. Next reaction, it is Cannizzaro reaction. This is dismutation reaction because during this reaction is formed oxidated and reducted aldehyde. This reaction is usual for aromatic aldehydes that don't have hydrogens at alpha carbons. This reaction is possible for formaldehyde and for aliphatic aldehydes, but that are substituted at alpha position and don't have hydrogens there. Because in another case, in alkali medium that we use for this reaction, we can observe aldolic or crotonic condensation. The mechanism of this reaction starts from the addition of high OH minus to the carbonylic group. We obtain such an anion with negative charge at oxygen, and then the next molecule of aldehyde with its carbon of carbonylic group reacts, and we have carboxylic acid anion and alcohol. And here on this picture is shown how this reaction is possible. OH is added, then next to H takes hydrogen, then the next molecule of aldehyde interact with this molecule and takes hydrogen, and we obtain carboxylic acid and anion of alcohol, and then is added hydrogen from the water. Perkin reaction is very similar with aldol condensation. This reaction occurs when aromatic aldehydes interact with acid anhydrides. And product is very similar with product in crotonic condensation. Is formed alpha, beta, unsubstituted acid. This is one method how we can obtain crotonic acid, cinnamic acid. So what occurs during this reaction? In acidic medium, acetaldehyde lose one proton here and became negatively charged. Similar anion we observed when we discussed aldol condensation. Yes, here was oxygen, here was hydrogen. And then this particle with negative charge that is formed from acetaldehyde attack molecule of aromatic aldehyde, and then is formed product of condensation with negative charge on oxygen, and then after hydrolysis firstly is evolved water here from this oxygen, and here is evolved water, and then after hydrolysis we obtain cinnamic acid. Benzoene condensation, the same is possible for aromatic aldehydes in the presence of cyanide anions. And the result looks as if two aldehydes react with each other head to head. If we name this aldehyde group head, yes, head to head. What is formed during this reaction? First stage, this addition of cyanide with formation anion. Then this anion is able to have resonance structure with negative charge at carbon. This hydrogen is transferred to oxygen, and here is negative charge at carbon. Then this negatively charged carbon atom interacts with partial positively charged carbon of next molecule of aldehyde and is formed product of addition. And then in this product cyanide is released and hydrogen that was here transferred to this negatively charged oxygen, and here is formed double bond. And after reaction we have backward cyanide anion. Reactions of aromatic aldehydes with halogens, this is the difference from aliphatic aldehydes. They occurs in the carbonyl group. Here this hydrogen is replaced by chlorine or another halogen. And substitution electrophilic occurs in the aromatic ring in meta position because aldehyde group is second type orientant and next substituent into the meta position. Thank you for your attention.